So we'll take here a few examples on the maximum principal stress theory so that our concept of the factor of safety if the principal stress is lying in the different quadrant will be get clear. Principal stress in a cast iron body are 40 megapascal tensile and the 90 megapascal compressive. The third principal stress being 0, find the factor of safety based on elastic limit if the criteria of failure is principal stress theory. The elastic limit in a simple tension is given as 80 megapascal and in simple compression is 450 megapascal for cast iron. Cast iron is a brittle material and for brittle material the SYT is same value is equal to SUT and we have SYT is equal to 80, so SUT is equal to 80 and SYC is equal to 450, so we have SUC is equal to 450. Out of two principal stress here, absolute value of compressive stress is a higher value that equal to 90 that will assign as sigma A and the lower value will assign to sigma B. Since the cast iron is a brittle material, we have SYT is same as equal to SUT. That value is equal to 80 megapascal. 80 megapascal. And SYC, yield stress in compression is same as ultimate stress in compression is equal to 450 megapascal. Now out of 40 and 90, 90 is the highest value, so that will assign to sigma A. So sigma A equal to minus 90. Always use the absolute value and the maximum absolute value will assign to sigma A. In that case we have sigma B, the other principal stress will be equal to 40 megapascal. 40 megapascal is tensile and 90 megapascal is compressive. We have to find out here factor of safety for principal stress theory, that is the maximum principal stress theory. You have to use this. So we'll develop the stress envelope here. For this purpose we'll take sigma A on x-axis, sigma B on y-axis. We have SUT is equal to 80. So this value corresponds to SUT and we have SUT is equal to 80. Same value of SUT you have to mark on positive of sigma B axis. So we have SUT is equal to 80. Then SUC you have to mark on the negative of sigma A axis, that will be equal to 450. So we have SUC is equal to minus 450. And one value you have to mark here, which is SUC is equal to 450. But you have to take this value as a negative value. Now we'll plot here the point A. Point A is minus 90 megapascal is a principal stress A. So principal stress A we can mark somewhere here, which one is minus 90 megapascal, and sigma B we can mark as 40 megapascal. So this one is 40 megapascal. Correspondingly we have a point in the second quadrant. If you have a point in the second quadrant, then we have to find out here two factor of safety. One is based on sigma A and one is based on sigma B, because we have two different boundary. One is boundary is SUT and other boundary is SUC. So factor of safety N1 we will calculate based on sigma A. Sigma A is a negative value, so we have to use the compressive ultimate stress SUC divided by absolute value of sigma A. SUC is same as equal to 450. So we have 450 divided by sigma A, which is equal to 90. So one value of factor of safety we obtained equal to 5. Then the second factor of safety you have to calculate based on sigma B. Sigma B is tensile in nature, so you have to use SUT divided by sigma B value. SUT is given as 80, so we have 80 divided by sigma B is equal to 40. So in this case we have factor of safety equal to 2. By rule you have to select the minimum value of N1 and N2. So we have factor of safety N is minimum of N1 and N2, that is equal to 2. So we have factor of safety is equal to 2. The stresses in a body are as shown in figure. Find the factor of safety based on elastic limit if the criteria of failure is a principal stress theory and we have given the value of SUT and SUC. You have to read this figure here. The value of sigma x is a compressive that equal to 410. So we have sigma x equal to minus 410 megapascal. Sigma y is downward, that is a negative of y axis, so that is also compressive. In this case, we have sigma y is compressive is minus 275 megapascal. And the shear stress is shown on the right face, which one is positive face, is acting along the positive of y direction. So value of tau xy we have to take as positive, and we have given the value of tau xy is equal to 240 megapascal. So the state of a stress is known to us, so we'll calculate here the two principal stresses, and then we'll select out of two principal stresses which one is the absolute maximum. We'll assign equal to sigma a, and the other value we'll assign as sigma b. Then we'll plot a stress envelope for maximum principal stress theory. So first of all, we'll calculate here the value of sigma average. So we have sigma average. Sigma average is same as equal to sigma x plus sigma y divided by 2. In this case, we have sigma x equal to minus 410, sigma y is equal to minus 275, and whole thing is divided by 2. So we'll get a sigma average equal to is minus 342.5, minus 342.5. We'll continue this practice of calculating the principal stress, because very quickly using sigma average and the radius we can draw the Mohr circle. That one is a useful idea in the case of maximum shear stress theory. So we have radius is same as equal to tau max, and we have tau max is equal to under root of sigma x minus sigma y divided by 2 whole square, plus we have tau xy square. That is, we have under root of sigma x is equal to minus 410, minus minus become plus, sigma y is equal to 275 divided by 2, and we have a square of it, plus we have tau xy, which one is 240 square of it. So we have tau max is same as equal to 249.3, 249.3. So minus 342.5 and 249.3, that will give you smallest value, and minus 342.5 and minus 249.3, that will give the largest value. So we'll assign the value of sigma a equal to sigma average minus tau max. We have sigma average equal to minus 342.5 and minus of tau max, which is 249.3. Always remember the value of sigma a magnitude wise must be the larger value. So value of sigma a will be equal to minus 591.8. That will be the compressive value in megapascal. Similarly, we can calculate sigma b. That will be equal to sigma average plus tau max. Second principal stress sigma b will be lower value. So we have minus 342.5 and we have plus 249.3. So sigma b will be the lower value, and sigma b is also negative, is minus 93.19. So both the principal stresses come out to be negative, so they will lie in the third quadrant. So the stress envelope for MPST, that is the maximum principal stress theory. This time we have value of sigma a is negative, that is minus 591.8, which is less than the value of SUC. So we have given here the value of SUC is equal to 760, and SUT is given as 210. So negative value of sigma a will plot on the left hand side, somewhere will be here, that will be minus 591.8, and sigma b is also negative value, is minus 93.19, will be marked somewhere here. So this one is minus 93.19, Because of both negative here, the point will lie in the third quadrant, and if the point will lie in the third quadrant, both the limit are remain same. So out of sigma A and sigma B, you have to select the maximum principal stress. So we have factor of safety will be equal to SUC, and this time the sigma A value is a higher value. Absolute value of sigma A is greater than absolute value of sigma B. So maximum principal stress you have to select here, that will be the absolute value of sigma A. In this case, the factor of safety will be equal to SUC, which is equal to 760, and absolute value of principal stress A is 591.8. 591.8 is close to 1.248, or approximately equal to 1.25. Stress in a body are as shown in the figure. Find the factor of safety based on elastic limit criteria of failure, again same, that is a maximum principal stress theory. We have given the value of SUT equal to 200, SUC is equal to 650. Now we have to read this figure here. The sigma x is shown outward, that is a positive value. So we have sigma x equal to 125, tau xy is also positive value because we are on the positive phase and going towards the positive of y direction. Whereas the 80 megapascal is a stress acting along the y direction, is acting along the negative of y direction, so it's a compressive stress. So sigma x is a tensile will be equal to 125 megapascal. Sigma y is compressive, so it is taken as negative minus 80 megapascal, and tau xy is positive value is 55 megapascal. Again we calculate here the two principal stresses. So first we calculate here sigma average and tau max, that is the radius. Sigma average is the same as sigma x plus sigma y by 2. So we have sigma x is equal to 125 plus we have sigma y is equal to minus 80 and is divided by 2. So we get the value of sigma average equal to 22.5. Next we calculate the maximum shear stress or the radius of Mohr circle. Tau max is same as under root of sigma x minus sigma y by 2 whole square plus tau xy square is equal to under root of. We have sigma x is equal to 125. Sigma y is negative, negative, negative become positive is plus 80 is divided by 2, and we have whole thing square. Plus we have tau xy is equal to 55 square. So maximum shear stress will come out to be 116.3 megapascal. Now sigma average is a positive value here, as well as tau max here plus minus 116.3. So if you take the two positive value, you will get the maximum value of a principal stress that we assign as sigma A, and one positive, one negative, that will assign as a second principal stress sigma B. So whichever is the maximum will be sigma A. So this time both are positive. Hence we'll select the sigma A equal to sigma average plus tau max, that is the same as radius. Sigma average equal to 22.5 and tau max equal to 116.35. So the principal stress sigma A will come out to be 138.8, and sigma B will consider as a second value is a lower value. This time we have sigma average minus tau max. Sigma average equal to 22.5, and we will select the negative value of the shear stress is 116.35. So sigma B is always lower value as compared to sigma A. This time our answer is minus 93.82. So this one is a standard stress envelope in the case of maximum principal stress theory. We have to look at the 2 point. One is sigma A, which one is a positive value is 138.8, and we have given the value of SUT is equal to 200. So we have SUT is equal to 200 megapascal and SUC is equal to 650. Sigma is a positive value, so we'll mark it on the positive of sigma A axis. Somewhere here will be equal to 138.8. And the sigma B is a negative value, so on the negative of sigma B we'll mark second value somewhere here will be equal to minus 93.82. So if I extend this line, in that case our point will be in the fourth quadrant. And in the fourth quadrant we have two limits. One limit is SUC and second limit is SUT. So based on SUT you have to select the tensile stress, and based on the negative value you have to select the compressive stresses. So for quadrant 4 we have to calculate two factor of safety. If you select SUC, then you have to select the compressive stress. This time the compressive stress is sigma B, so you have to select the absolute value of sigma B. Ultimate compressive stress is given as 650. So we have 650 divided by sigma B is 93.82. This will give you one value of the factor of safety is 6.93. Second factor of safety will calculate on the base of SUT. This calculation you have to do for quadrant 2 and quadrant 4 only. Since SUT is a tensile in nature, we will divide it by tensile stress equal to sigma A. SUT is given as 200 and sigma A is equal to 138.8. Find out this value of factor of safety. You will get this value is equal to 1.44. So when we are in the quadrant 2 or quadrant 4, you have to select the factor of safety as a minimum value of either N1 or either N2. This time the minimum value is 1.44. So factor of safety will be equal to 1.44. So in each problem what we are doing, we are changing the value of sigma x, sigma y and tau xy such that we are getting the point in the quadrant 1, quadrant 2, quadrant 3 and 4. That will help us to improve the concept of finding the factor of safety in the case of maximum principal stress theory. So let's consider here we have a state of a stress is shown as in the figure, and we want to find out again the factor of safety based on the maximum principal stress theory. This time SUT is given as 205 and SUC is given as 650. So you have to read this figure carefully. Sigma x is same as 14 megapascal is tensile. 70 megapascal is sigma y, which one is again tensile. On the right face, the shear stress is acting in the downward direction, so it has to be taken as a negative value. So we have a stress acting along the x direction is a tensile is positive value is 14 megapascal. Stress acting along the y direction is also tensile, so we'll take it as positive value is equal to 70 megapascal. And the shear stress acting tau xy on the right face in the downward direction, so we'll take it as a negative is minus 20 megapascal. Again, your first job is to calculate the principal stress sigma A and sigma B. For that we require sigma average and the tau max or the radius of a Mohr circle. Sigma average is given as sigma x plus sigma y by 2. This time we have sigma x is equal to 14. So we have 14 plus 70 divided by 2. 84 divided by 2. So we have sigma average will be equal to 42. Then we calculate here the tau max, which is same as equal to radius of Mohr circle is under root of sigma x minus sigma y by 2 whole square plus tau xy square. So we have under root of sigma x. Sigma x is equal to 14 minus 70 divided by 2 whole square plus tau xy is equal to minus 20, and we have square of it. Tau max will be plus minus here is equal to 34.41 megapascal. Using tau max and sigma average, we will calculate two values. This value is positive. Positive and positive will give the value of sigma A. Positive and negative will give the value of sigma B. To find out the one of the principal stress here, we will select both value positive. So sigma A is equal to sigma average plus we have maximum shear stress equal to tau max. Sigma average is equal to 42. And the maximum shear stress equal to 34.41. So in this case value of sigma A is equal to 76.41. Similarly, the second principal stress will be minimum value. Therefore, we'll select the negative value of the maximum shear stress. So we have minus of tau max. Average shear stress equal to 42 minus 34.41. So this value is also positive. that is equal to 7.591. So we'll use a stress envelope for maximum principal stress theory. Already we know the value of SUT. SUT you have to take as equal to 200, and the value of SUC you have to take as 650. Both sigma A and sigma B are positive values, so the point will lie in the quadrant 1. Sigma A is very close to 80, so this value will mark somewhere here, and we have sigma A equal to 76.41. Contribution of the second principal stress is very small, so that value we can locate as 7.591. Since we are in the quadrant 1, both the boundary are SUT, so maximum principal stress will decide here the factor of safety. Out of sigma A and sigma B, the maximum principal stress is sigma A, factor of safety is, and we have SUT divided by the maximum value of the principal stress equal to sigma A. SUT is equal to 200, and we have value of sigma A is equal to 76.41. 200 divided by 76.41, so in this case we get the factor of safety is close to 2.68. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.